All right, so let's practice this a little bit more here. We want to find a parametric equation, but so far we've done a circle has a nice sweet formula, the lines have nice sweet formulas. What if I don't have this nice sweet little formula here? What if I want to find the segment of a parabola? And I'm given y equals 9 minus x squared, and specifically this segment is being taken from -1, which is less than or equal to x, which is less than or equal to 3. All right? If you don't have a sweet little formula, then you just make your own. When you make your own, you're going from this inside function. So I'm just going to say, okay, x equals t. It's literally that easy. So if x equals t, then y is equal to 9 minus t squared. And if x equals t, my parameter goes from -1 to 3. And whammo jabammo, you just did it. All right, if you don't have that set up formula for you, generically how you come up with these parametric equations is you just take that inside function and set that equal to your t. For instance, if I have x is equal to y minus 5 squared plus the square root of y, and I want to look at this in terms of the complete curve. All right, the complete curve. You're not going to go around and try to solve that thing for y. That's nuts. So when you set up your parametric equations, that's no big deal. I'm just going to make my y equal to t. And if y is equal to t, then x is equal to t minus 5 squared plus the square root of t. Now, if I'm talking about my complete curve here, think about what my parameters are on t. Can t go from -infinity to +infinity? No, right? Because look at this. So t has to go, or t has to be greater than 0. So it's going t is greater than or equal to 0. And that's it. If you have some freaky functions, no problem. Set your t equal to that inside function and go with it. All right? Cool. Easy peasy. Now, we've done lots with parametric equations. Let's take a little derivative. Derivatives here of our parametric curves. I'm going to let x equal f of t and y equals g of t. All right, so I have these are just my parametric equations. You know that f is a function of t and y is a function of t. So if I'm actually going to find my derivative is dy dx, right? But if these are in terms of t, then it's dy dt divided by dx dt. Pretty sweet, right? So g prime of t over f prime of t. Basically what you're doing is you're just taking the derivative of your y and divide it by the derivative of your x. dy dx. The derivative of the y over the derivative of x. That's it. That's it. How nice is that, right? Yeah. Okay, so let's do it right now. So if I have example 6 here, I want to determine the horizontal and vertical tangent lines. Okay, so for this, here's A. X equals t and y equals 2 square roots of t for t greater than or equal to 0. Sweet. Okay, so when I find my derivative, you know your horizontal and vertical tangents. Your horizontal tangent happens when your derivative equals 0, right? That's your horizontal tangent. So maybe let's write that out so that we can remember this. So horizontal tangent, let's change colors. This is when your derivative equals 0. For your vertical tangent is when your derivative is undefined. Yikes, I smashed that in there. Let me try to move it to the different line. That might look better. Okay, so your horizontal tangent, because it's a slope. What's a derivative? Slope of your tangent line, right? So if I have a horizontal slope is 0. A vertical slope is undefined. A derivative is just the slope of your tangent. So we're just looking at these tangent lines and the basics of slopes. Okay. So the first thing we need to do is come up with a derivative. Anytime you see tangent, immediately go to derivative. So dy dx here is going to be the derivative of my numerator. So I have 2 times this 1/2 t to the negative 1/2 over the derivative of t is 1. So what I really have is 1 over the square root of t. And t can obviously not equal 0 because it's in that denominator. All right, so let's look at what's going down right here. Since dy dx is equal to 1 over the square root of t, and is there any possible way, I should label this, horizontal tangent. I want to say for this derivative, I want it to equal 0. Is there any possible way that's ever going to equal 0? No. If you have a number in the numerator, there's no possible way, because a 0 is 0 divided by something, right? There's no variable up there. So this is never going to equal 0. So for this problem, there is no horizontal tangent. Okay, do I have a vertical tangent? I don't know. Is there some place that this is going to be undefined? Vertical tangent. I'm asking, where is the derivative undefined? Right? Is there a place that I have this derivative, dy dx, 1 over the square root of t, to be undefined? Yes, yes. When t equals 0, the derivative is undefined. Therefore, you have a vertical tangent. When t is equal to 0, then you plug that in. When t is equal to 0 at the coordinate point. So if t is equal to 0, and I'm plugging that in, what are my x and y coordinate point associated with t is equal to 0? The point 0, 0. At the point 0, 0. All right, so a vertical tangent is happening at that specific point, and there is no horizontal tangent on this particular problem. You see that? Okay, let's do one more. And rock the socks off this thing. I want to find the horizontal and vertical tangents. This is part B. Okay. X is equal to 4 cosine t. Y is equal to 16 sine t. And 0 is less than or equal to t, which is less than or equal to 12. All right? So let's do this thing. I want to first find the derivative. So my derivative here of dy dx is going to be the derivative of the numerator, which will be 16 cosine t, over the denominator, which would be negative 4 sine t. So if I'm looking at this, cosine over sine is cotangent. All right, so that's my actual derivative, negative 4 cotangent t. So if I want to find that horizontal, that's where you set your derivative equal to 0. So I have negative 4 cotangent of t is equal to 0. So divide both sides by negative 4. Nobody cares about that. Cotangent of t equals 0. Now my question is, where is cotangent 0? And I know that cotangent is cosine over sine. So what I'm looking for is when is cosine 0. So where is cosine 0? Yep, pi over 2 and 3 pi over 2, right? So that's what we're looking for. So at pi over 2 and 3 pi over 2. So if I want to know the points that go with those values where I have a horizontal tangent, you have to plug that back into the original. So at t is equal to pi over 2, then I'm plugging this in. X is equal to 4 cosine of pi over 2. So x is equal to 0. Y, so that's a x, is equal to 16 sine of pi over 2. So the sine of pi over 2 is 1. So y is 16. I have the point 0, 16. All right. So I have a horizontal tangent at the point 0, 16. Now let's figure out what's happening at 3 pi over 2. X is equal to 4 cosine of 3 pi's over 2. Well, x is 0. That's nice and easy. Y is equal to 4 sine of 3 pi over 2. Oh, sorry, not even a 4. 16 sine of 3 pi over 2. So y is now equal to 16 times negative 1, which would be negative 16. So I have the coordinate point 0, negative 16. I'm going to get rid of this fluffy little jobber here because that's throwing me off. I should just put a box around it. I don't know what I was thinking. So I have these two coordinate points. At those two coordinate points, there are horizontal tangent lines. Therefore, there are horizontal tangent lines at the point 0, 16 and 0, negative 16. Horizontal tangent. Set that derivative equal to 0. Now, if I want to find a vertical tangent, this is when I want to determine where is this undefined. When is negative 4 cotangent of t undefined? That's what I'm really looking for here. Well, let's think about this here for a second. I have asymptotes, right? Where are my asymptotes for cotangent? Yes, and I do also have, and so think about it, I'm going to swing this down just a little bit. Also, I have asymptotes where it's undefined, is you can tell me where sine is equal to 0. That's where I have asymptotes in cotangent. So everywhere where sine is equal to 0, that is what we're going for. So I know that t is equal to 0, 2 pi, because it's the same shot there, and t is equal to pi, because that is where sine is 0. So that's what makes this undefined. That's where my vertical asymptotes are for cotangent. All right, so now let's see the coordinate points that are associated with that. at, what's the first one? T is equal to 0, 2 pi. You see 0 and 2 pi are the same, right? They're coming to the same spot. Okay. So x is equal to 4 cosines of 0. So x is equal to 4. Y is equal to 16 sines of 0. So y is equal to 0. So I've got the point 4, 0. And then let's see what's shaken out here at t is equal to pi. X is equal to 4 cosine of pi. So that's -1, giving me a -4. Y is equal to 16 sine of pi. That's the beauty of these that go to 0. That makes it super easy, right? Kind of our best day ever. Therefore, there are vertical not asymptotes. There are vertical tangent lines at 4, 0 and -4, 0. So just take the derivative. It's just the I'm going to scoot this in. It's the derivative there of x, right? Pardon me, derivative of y over x. Just like any other slope, just like any other derivative, dy dx. Y's go on top. Just take the derivative of each one of those pieces, and then horizontal tangents, it's when your slope equals 0. That's what a derivative is, right? Slope of the tangent line. No problem. We have a vertical tangent. All right. No sweat. That's whenever you have your undefined. Where is this undefined? Just like a slope is undefined when it's a vertical. All right. 12.1 was fairly long. You guys got this. Hang in there. Now go practice this. I know you can do it.